We know that the sine rule says A by sine A is equal to B by sine B is equal to C by sine C is equal to 2R. As and when you have sine A by sine B, what is sine A by sine B? Is nothing but A by B. Sine A by sine B is equal to A by B. Sine B by sine C, that is, as and when you require the ratio of sines, you can easily have the ratio of corresponding sides. Sine C by sine A is equal to C by A. Yes, this is another consequence of sine rule. Now, let us turn our head towards another rule, namely cosine rule. This cosine rule generally will be expressed in two different forms. Some textbooks, some authors and some lecturers used to call the first rule as a projection rule or cosine rule 1. As you like it, you can have the name, and I like to introduce you by the name cosine rule 1. Cosine rule 1. What is that? Suppose you have a triangle like this. A, B, C. Let this be the altitude. Say D. This is A. This is A. Look here. From this A is equal to, you can write BD plus DC. Any problem? What is small a? BC. BC is nothing but BD plus CD. You can write BD as, what is BD? This is small c, this is small b. From this triangle, what is cos B? Please tell me. BD by C. So BD is equal to C cos B, isn't it? C cos B. What is DC? What is DC here? What is cos C? Cos C is DC by B. Therefore, DC is equal to B cos C. Hence, it is B cos C. So that we are able to have A is equal to B cos C plus C cos B. In a similar fashion, if you want to have B here, A is equal to B and C are coming here, both small letters and capital letters. Here we have B is equal to C cos A plus A cos C, and C is equal to A cos B plus B cos A. Like this, we state, we learn cosine rule 1. In this one, we have three different formulae for small a, small b and small c. If you want to have small a in terms of small b, small c and capital B, capital C, you can write like this. Small a is equal to B cos C plus C cos B, small b is equal to C cos C plus A cos C, and small c is equal to A cos B plus B cos A, like this. This is what we call cosine rule 1. Some students, some lecturers, some others say that this is a projection rule also. In respect of the name, the thing is you must learn them. You must remember them. Well done. Next, cosine rule 2. What does it say? Cosine rule 2. What does it say? In any triangle ABC, A square is equal to B square plus C square minus 2BC cos, this is A, this is A. B square is equal to C square plus A square minus 2CA cos B. C square is equal to A square plus B square minus 2AB cos C. This is cosine rule 2, and so many others say that this is the actual cosine rule. And the proof of this result, of course, it is a combination of 5 to 6 steps, and everybody knows about them. This is what we say about cosine rule 2 or simply cosine rule. There is a lot of set of applications for this one. This is very useful. From this you can have from this cos A is equal to B square plus C square minus A square by 2BC. Cos B is equal to C square plus A square minus B square by 2CA, and cos C is equal to A square plus B square minus C square by. These are also important deductions from this cosine rule. As and when you need to use cos A, cos B, cos C in a problem given, you can use this formula for cos A as B square plus C square minus A square by 2BC, cos B as C square plus A square minus B square by 2CA, cos C A square plus B square minus C square by 2AB. Not only that, you just send this A square to that side and 2BC cos A this side, so that we have 2BC cos A is B square plus C square minus A square, and 2CA cos B is equal to C square plus A square minus B square, and 2AB cos C is equal to A square plus B square minus C square minus C square. Yes, this is what we say about cosine rule 2. And let us now use the applications of this cosine rule. This cosine rule is directly useful in obtaining half-angle formulae. What do you mean by a half-angle formulae? Formula regarding sin A by 2, sin B by 2, sin C by 2, cos A by 2, cos B by 2, cos C by 2, and tan A by 2, tan B by 2, tan C by 2. To obtain such things, this cosine rule is very much useful. Let us look at one of such things. What is sin square A by 2? What is sin square A by 2? Is nothing but 1 minus cos A by 2. But we know that what is cos A? What is cos A? B square plus C square minus A square by 2BC whole divided by 2. So this is 2BC minus B square minus C square plus A square by 4BC, isn't it? So this is nothing but A square minus of B minus C whole square by 4BC. Again, this can be taken as A square minus B square, A plus B minus C into A minus of B minus C by 4BC. You see, this is nothing but 2S minus 2C, and the other is 2S minus 2B by 4BC. So that if you can cancel 2 and 2, altogether 4 you can cancel, you can have, what do you have here? S minus B into S minus C by BC. So as a result, this is sin square A by 2, and if you want to have sin A by 2, under root it is. Moreover, plus or minus or plus. A is an angle of a triangle. It is less than 180. So A by 2 is less than 90. Hence A by 2 is surely acute. Therefore sin A by 2 is equal to positive square root of S minus B into S minus C by BC. After noting down the formulae for sin A by 2, sin B by 2 and sin C by 2, now we shall turn our head towards obtaining the values of cos A by 2, cos B by 2 and cos C by 2 now. Yes, let us obtain the value of cos A by 2. From the knowledge of earlier trigonometric ratios and identities, we know that cos A by 2 is equal to plus or minus root of 1 plus cos A by 2. You see, ABC is a triangle, so A by 2 is surely acute. Why? Because A plus B plus C is equal to 180. So A by 2 plus B by 2 plus C by 2 is 90. So A by 2 is surely less than 90. Okay, right. So as it is acute, A by 2 lies in the first quadrant, and in the first quadrant every trigonometry ratio is positive, so you need not consider plus or minus here. We just take plus root of 1 plus cos A by 2. 1 plus, come on, what is cos A? What is cos A? From cosine rule 2 of the same chapter, that is properties of triangles. What is cos A? Cos A is nothing but b square plus c square minus a square by 2bc whole divided by 2. Okay, this is nothing but root of LCM is 2bc into 2 is 4bc. 2bc plus b square plus c square minus a square. Isn't it? Excellent. So it is root of 2bc plus b square plus c square. What can it be? It is nothing but b square plus c square plus 2bc minus a square by 4bc. Okay, it is b square plus c square plus 2bc. What is it? b plus c whole square. Hence this is equal to root of b plus c whole square minus a square by 4bc. Again, this b plus c whole square minus a square looks like x square minus y square. So it can be simplified as x plus y into x minus y. So, come on, this can take the form root of b plus c plus a into b plus c minus a by 4bc. Again, what is b plus c plus a? A plus b plus c. What is a plus b plus a? It's just nothing but 2s. Of course, b plus c minus a can be taken as a plus b plus c minus 2a. That is 2s minus 2a. Hence it is 2s into 2s minus 2a by 4bc. Well, my dear, here it is 2. You can get it 2 as a common factor from this bracket. Total it becomes 4. That 4 and this 4 can be cancelled. At last, what could you have? S into s minus a by bc. Well, friend, we have succeeded in obtaining the value of cos a by 2. What is cos a by 2? Cos a by 2 is therefore equal to root of s into s minus a by bc. Cos a by 2 is equal to root of s into s minus a by bc. So, likewise, in a similar fashion, you can be in a position to have cos b by 2 and cos c by 2 also. So, we could have proved that cos a by 2 is equal to root of s into s minus a by bc. In a similar fashion, cos b by 2 is equal to root of s into s minus b by ca, and cos c by 2 cyclically in a similar fashion we have s into s minus c by ab. Well done. Let us gather the previous sin a by 2, sin b by 2, sin c by 2 also at a stretch on the screen. Let us have sin a by 2 is equal to square root of s minus b into s minus c by bc. Sin b by 2 is equal to square root of s minus c into s minus a by ca. Sin c by 2 is equal to square root of s minus a into s minus b by ab. We have all the 6 formulae regarding sin a by 2, sin b by 2, sin c by 2 and cos a by 2, cos b by 2, cos c by 2 are there before us. They are ready to be used. By making use of them, we can find tan a by 2, tan b by 2 and tan c by 2 also in terms of s and s minus c, s minus b, s minus c, like that. How can they be obtained? Look here, tan a by 2. What is the basic formula for tan a by 2? It's nothing but sin a by 2 by cos a by 2. There is sin a by 2, here is cos a by 2. You can use them directly. Come on, use them. That by this, what is going to happen? BC and BC will be cancelled, leaving you, come on, root of s minus b into s minus c by s into s minus a. Tan b by 2 is equal to root of s minus c into s minus a by s into s minus b. Tan c by 2 is equal to root of S minus A into S minus B by S into S minus C. These are very familiar, very useful, very important formulae in probabilities of triangles. Altogether they are called with a famous and common name, that is a half angle formulae. A by 2, B by 2, C by 2. Sin A by 2, cos A by 2, sin A by 2, sin B by 2, sin C by 2, cos A by 2, cos B by 2, cos C by 2, and tan A by 2, tan B by 2, tan C by 2. Well, friends, regarding this tan A by 2 and tan B by 2 and tan C by 2, we can make use of one more standard formula, that is delta is equal to root of S into S minus A into S minus B into S minus C, which is a famous formula which is also called Arrow's formula. Tan A by 2 is equal to root of S minus B into S minus C by S into S minus A. Accordingly, tan B by 2 is equal to square root of S minus C into S minus A by S into S minus B, and tan C by 2 is equal to square root of S minus A into S minus B by S into S minus C. Well, let us make use of the formula delta is equal to root of S into S minus A into S minus B into S minus C, which is of course called Arrow's formula. Yes, for area of a triangle. Okay, look here. This can be written as you multiply with S into S minus A on both numerator and denominator. What is going to happen? S into S minus A into S minus B into S minus C by S square into S minus A whole square. Well, my dear, you please observe the numerator. It is just nothing but delta, isn't it? By root of S square is S and the root of S minus A whole square is S minus A. So, the simplified formula of tan A by 2 is equal to delta by S into S minus A. In a similar way, tan B by 2 is equal to delta by S into S minus B, and tan C by 2 is equal to delta by S into S minus C. Moreover, the benefit which we have by noting this simplified form is you can be in a position to have cot A by 2, cot B by 2, cot C by 2 directly. What is cot A by 2? It is just nothing but the reciprocal of tan A by 2. So that we have cot A by 2 is equal to S into S minus A by delta. Cot B by 2 is equal to S into S minus B by delta. And cot C by 2 is equal to S into S minus C by delta. With this, the total list, the complete list of half angle formulae is over. Yes, here we could have made use of a beautiful formula, namely delta is equal to square root of S into S minus A into S minus B into S minus C. Let us observe its proof. It's a single line proof, of course, or at most two lines. Very, very simple. Let us observe it. Yes, according to our plan, we would like to know the proof or the reason behind the saying delta is equal to root of S into S minus A into S minus B into S minus C. Actually, what is delta? Area of a triangle. Using the famous formula half BC sin A, what is delta? Area of the triangle is half BC sin A. Hence it is half into BC into, what is sin A? 2 sin A by 2 cos A by 2. Cos A by 2 is therefore equal to half into BC into 2 into, what is sin A by 2? Root of S minus B into S minus C by BC. What is cos A by 2? Root of S into S minus A by BC. Root BC becomes BC, to be cancelled with BC. Again, half and 2 go away, leaving you root of S into S minus A into S minus B into S minus C. That's it. That is the beauty of that formula. Delta is equal to square root of S into S minus A into S minus B into S minus C. Yes. After noting down sine rule, cosine rule, now this is our turn to look at tangent rule. This is also called Napier's formula. What is that? Tan of b minus c by 2 is equal to b minus c by b plus c cot of a by 2. Of course, this can also be taken as tan of b plus c by 2. Yes, because b plus c by 2 and a by 2 are complementary, isn't it? Therefore, like this, or another way to write is b minus c by b plus c tan of b plus c by 2. Yes, you can. Like that also you can write, because a by 2 and b plus c by 2 are complementary. These two are equal. So at this juncture itself, we can have this as b minus c by b plus c into tan of b plus c by 2. Isn't it? Okay, just like that, tan of c minus a by 2 is equal to c minus a by c plus a cot b by 2, and the same can also be taken as c minus a by c plus a tan of c plus a by 2. Tan of a minus b by 2 is equal to a minus b by a plus b into cot c by 2, or this can be again written as a minus b by a plus b into tan of a plus b by 2, like that. These three statements, similar statements, cyclic statements, of course, in the sense, the statements in which the letters come cyclically, okay, right, are called together called tangent rule or Napier's rule. This we rarely use in some problems. In some special problems only we are interested to make use of them. Have a note of that. Sine rule, cosine rule and tangent rule, they have been discussed. Now we like to turn our head towards the formula regarding different radii, that is capital R, small r, R1, R2, R3 according to their significance. Okay, let us first concentrate on R. What is R? From sine rule, a by sine a is equal to 2r, isn't it? Therefore, R is equal to a by 2 sine a. The same can be b by 2 sine b. The same can be c by 2 sine c. This is one thing. Another thing, R is equal to ABC by 4 delta. Already we could have done it, isn't it? R is equal to ABC by 4 delta. ABC by 4 delta. And again, R square is equal to delta by 2 sine A sine B sine C. Delta by 2 sine A sine B sine C. From where could you get this? Because we have had delta is equal to 2r square sine A sine B sine C, isn't it? From that we can have r square. Of course, by taking positive square root of that, you can have r. Yes, this is about r. And then about small r. Small r is delta by s. R1 is equal to delta by s minus a. R2 is equal to delta by s minus b. And R3 is equal to delta by s minus c. Delta by s minus c. This is one set of formulae. There are three different sets of formulae for these radii. These are similar. What I mean to say is they look alike almost with small changes. So this is the first set. What can we achieve from this first set? Look here. What is 1 by R1 plus 1 by R2 plus 1 by R3? What can you observe? What is 1 by R1? S minus A by delta, S minus B by delta, S minus C by delta. Isn't it? S minus A plus S minus B plus S minus C by delta. S plus S plus S, 3S. Minus of a plus b plus c, 2s. 3s minus 2s is s. S by delta. But s by delta is nothing but 1 by r. Hence, we are able to have a beautiful result regarding this. 1 by r1 plus 1 by r2 plus 1 by r3 is equal to 1 by r. So, if the 3 x radii are given, then it is of course an easy matter to find the in radius. 1 by r is equal to 1 by r1 plus 1 by r2 plus 1 by r3. That is next one. By making use of these formula again, what is 1 by r1 square plus 1 by r2 square plus 1 by r3 square? What can you have? 1 by r1 square is s minus a whole square by delta, s minus b whole square by delta, s minus c whole square by delta, isn't it? So, s minus a whole square plus s minus b whole square plus s minus c whole square by delta square. Good. If you can expand all those whole squares, you have s square at 3 places, 3s square, minus 2sa, minus 2sb, minus 2sc, minus 2s into a plus b plus c, plus a square plus b square plus c square by delta square. Isn't it? S minus a whole square plus s minus b whole square plus s minus c whole square. You see, if you can add 1 by r square also here, then s square will also come here. So that this is s square plus 3s square plus s square, 4s square, 4s square, 2s into 2s, 4s square, a plus b plus c is 2s, 2s into 2s, 4s square and 4s square will be cancelled, leaving you a square plus b square plus c square by delta square. So what is the ultimate result? 1 by r square plus 1 by r1 square plus 1 by r2 square plus 1 by r3 square. What is the answer? This is nothing but a square plus b square plus c square by delta square. This is regarding R1, R2, RR1, R2, R3 in view of these formulae. Well, let us concentrate on the second set of formulae. Small r is equal to s minus a tan a by 2. The same can be s minus b tan b by 2. The same can be s minus c tan c by 2. And r1 is equal to s tan a by 2. r2 is equal to s tan b by 2. And r3 is equal to s tan c by 2. This is the second set of formulae regarding r, r1, r2 and r3. And in some typical problems only, we are supposed to make use of these formulae. Of course, it is essential to everyone to get them remembered. You please have a look over that and you try to get them remembered. You remember them. The third set of formulae. Small r is equal to 4r sin a by 2 sin b by 2 sin c by 2. r1 is equal to 4r sin a by 2 cos b by 2 cos c by 2. r2 is equal to 4r cos a by 2 sin b by 2 cos c by 2. And r3 is equal to 4r cos a by 2 cos b by 2 sin c by 2. And it will be very easy also to remember them. In R, all the three functions available are sine functions, sin a by 2, sin b by 2, sin c by 2. In R1, the first place is occupied by sine function, the other two are cosine functions. In R2, the second place is occupied by the sine function and the other two, the first and last, are being occupied by cosine functions. Accordingly, automatically and symmetrically, in R3, the third place is occupied by sine function and the first two places are occupied by cosine functions. So, These are very much useful, widely in use. They have many applications. Let us now look at some of those applications. Look here. Let me first find R1 plus R2. What happens? You're supposed to add these two. What happens? What can be got as a common factor? 4R cos C by 2 can be got as a common factor. Into sin A by 2 cos B by 2 plus cos A by 2 sin B by 2 is nothing but sin of A plus B by 2. You see, A plus B by 2 and C by 2 are complementary. Therefore, sin A plus B by 2 can be replaced by cos C by 2. I think you could have followed my wording. A plus B by 2 and C by 2 are complementary. Therefore, sin A plus B by 2 is nothing but cos C by 2. Hence, it is 4R cos square C by 2. Why? Because this is cos C by 2, this is cos C by 2. Altogether, 4R cos square C by 2. Well done. Let us now take R3 minus R. What does it say? What happens? R3 minus R. In these two, what can you get out of that? What can you get a common factor? 4R sin C by 2. 4R sin C by 2 into, come on, cos A by 2 cos B by 2 minus sin A by 2 sin B by 2. Cos A by 2 cos B by 2 minus sin A by 2 sin B by 2. What is that? Cos A by 2 cos B by 2 minus sin A by 2 sin B by 2 is just nothing but cos of A plus B by 2. Well, my dear, just like in the previous case, A plus B by 2 and C by 2 are complementary. Therefore, cos A plus B by 2 can be replaced by sin C by 2. Good. So, sin C by 2 into sin C by 2 is 4R sin square C by 2. Well, my dear, you try to add these two. What is going to happen? R1 plus R2 plus R3 minus R is equal to 4R into cos square C by 2 plus sin square C by 2 is 1. Therefore, from this we have R1 plus R2 plus R3 is equal to 4R plus small r. Beautiful result. R1 plus R2 is equal to 4R cos square C by 2. R3 minus R is equal to 4R sin square C by 2. R1 plus R2 plus R3 is equal to 4R plus small r. These are all consequences of this formula. The so-called third set of formulae. The so-called third set of formulae. Yes. They're beautiful, they're useful, they're famous, they're important.